So welcome back, everybody, also online on the Twitch stream. I hope you had a nice break. I always do this very nice introduction here, not to bore you, but because the people online, they will need a minute or two to actually click on the stream again. But I think now they should be there. And I already have one question here. It was at the end of the last part. Is it common to reduce the two equations to a single one, or is there a reason to keep them as two separate equations? This is a very, very good question, and I intend to use the whole term to answer it. So sometimes you keep them as single ones, and sometimes you reduce, depending on what you want. But let me come back to the handouts and everything. So the point here is that in such a signal flow graph, you actually want to be able to calculate the transfer function, for example, from x to z. So Mason called that the gain. So this g you see here would be the answer to the question, what will you get at the output z here, given some value of the independent variable x. This is the transfer function. And what Mason said is that this gain here is actually possible. You can do that with a very simple rule. So at the bottom, you have, of this gain rule, you have the graph determinant. And at the top, you would have all the paths which go from the input you chose to the output you chose, and all of the subdeterminants. And now the graph determinant is the first one. For that, you have to find the loops. And don't panic, I will presently make an example for you. But you have to find the loops. And then the graph determinant is 1, and then minus the sum of all those loops. So you have to add those loops. And after you have done that, you have to go on and do plus the sum of the products of all combinations of two loops that have no nodes in common. So you will have to find the loops and see which ones do not touch each other, and then also put the sum of all those products. And then you have to do minus the sum of the products of all combinations of three loops that have no nodes in common. And after you have done that, you will have to do the sum of the products of all four loops, and so on. It actually never stops. Now you wonder, isn't that something a little bit stupid? I mean, the effort you do there, it can really escalate. Now, however, if anybody builds an electronic system with feedback, the idea they normally have is that they want interacting feedback loops. So having one feedback loop here and one feedback loop here and one here, if they do not touch each other, it's just three independent systems or something like that, yes. They only get efficient and give you new behavior in a system if they touch. So the most common thing of a signal flow graph or an equation system behind which describes a system engineers use is that the loops are not independent. And then the Mason gain rule will start on the first or on the second line, sometimes on the third line, but mostly the first or the second. If you go and write these equation systems as matrices, you would find that the matrix representation then has a system matrix which contains a lot of zeros. This is very common for electronic systems. It's called a sparse matrix. So Mason's gain rule is actually a way to have an efficient sparse matrix solution of this equation system without writing down the equations. And this is why it is also sometimes used in the background in symbolic algebra tools. For you as the user, the idea is really, if you want to do that, you have to find all of the paths through that, and all of the loops, first the loops. Now, there is something very wonderful. The denominator of your transfer function, which you have here, the delta, there you only need loops. This means for any such transfer function, what is in the denominator doesn't depend on what is the input and what is the output. It's just what are the loops. And now you know that most of the stability of a function depends on its poles. The poles are in the denominator. So generally speaking, it is enough to look at the loops of any such graph to find out whether a system is stable. And then it is stable for any input-output combination. The pi are the forward paths, and the delta I are the subdeterminants here. So the forward paths are also quite easy. You check how you go from the input to the output. I will make an example in 1 minute. And the subdeterminants, the delta I, which are in this sum, they are the same as the graph determinant, but you simply have to remove all of the loops that are somehow have a node in common with any of the paths. So you take the whole graph determinant and then you say if the path touches all loops, then the subdeterminant is 1. If it fails to touch one of them, then it is not 1. An example is in order. And this example is on the next page. The example above here is quite simple. That's the one I did. Let's make the more complicated example right now. If I take this complex example, then I will find some loops. What is a loop? A loop is when I can start from a node and somehow turn around and go back. So this is the loop number 1, which I find. Please see the signal flow graph as a one-way system. So it's like if you're driving your car in Zurich, there are lots of one-way streets. And if you never must walk against the one-way or drive against the one-way. In the world out there, if you do that, you will get probably your driving license revoked. I don't know what the punishment is. In here, there is also punishment for walking against the arrow. It's the incorrect result and the lower grade in the exam. So never against the arrow. But if you remember that, then you can always find all of the ways how to drive in circles. So another way to go in circles here would be this one. So you start here and walk around here. This is the loop number 2. And then a third loop is you start here, walk around here. This is the loop number 3. And the loop gains is just everything you find along the way, you multiply it. So here it is E times H. And this is how you calculate the loop gains. Now the graph determinant here, I have already written it with the loops, but let me write it without the loops first. So without inserting, so the delta, according to Mason, is 1 minus the sum of all loops. I have 3 of them. And then plus all products of 2 loops that do not touch. And now I find that the loop 1 and the loop 2, they do have nodes in common. So L1 and L2 is not the product I now need. But loop 1 and loop 3 do not have a node in common. So I have L1, L3. And also the loop 2 and the loop 3 have no node in common. So I have L2 and L3 also as a product here. And the line you have down here is just the same thing inserted. Okay. It doesn't really make a lot of sense, this example. It doesn't have a physical equivalence because all the weights are just A, B, C, D, and so on. Yeah, but this is only to show you how the loops work and the paths work, because now come the paths. How many paths do I have? On how many distinct ways can I get from X to Y? So one way is to go here. This is the first path, P1. Yeah, you can almost read it. And this goes through everything, A times B times C times D times E, so this is its weight. But it also touches all of the loops. So in order to have the subdeterminant for the path 1, I take the graph determinant and remove any expression with any of the loops the path touches, which are all of them, so it's just a 1. This is not the same story for the second path. The second way to get through this here is here, like so. So this is the path 2. And now the path 2, you can see it bypasses the loop 1. With the loop 2, it has one node in common. So this I delete again. But with loop 3, it has all nodes in common, but loop 1, it does not touch. So therefore, the graph determinant for that case here would be that you say 1, and then you take from the original graph determinant everything but loops that are touched are removed. So L2 is touched, is removed, L3 is removed. Here you have L3 in it, here you have L2 in it. So everything you have to remove except the single term L1 here. So this is 1 minus L1. And then you insert everything and you have the transfer function. And I can only motivate you to do that always by hand, to find the original values, maybe not insert everything, but find the original structure of the graph, find the loops, find the paths, because it will be so important for you to see that when you want to design something, when you want to design a system. So with some experience, this view of the graphs will allow you to get a better idea of what a system is actually doing. So in my work, it has helped me a lot. If I do the graph of a system, I even can construct things. I can say, oh, it looks like a graph of something else, but if it had one loop more or another path, it would be more flexible or so, something like this. And then it helps me actually construct new stuff. Yeah. So I must motivate you to do that by hand, but then maybe control it, check it, whether it is correct. And there I have a very good surprise for everybody who heard about this lecture before, especially also for Raphael. Students always kept telling me, wouldn't it be nice if there was a tool? But it is, of course, very hard to program a tool like this. But at the university where I normally teach, this is the University of Applied Sciences, Northwestern Switzerland. So I'm only an external teacher here at ETH. At that university, we have a close cooperation also with the informatics people. And there were 2 bachelor students which for their final project chose to implement a signal flow graph tool, it was the meaning from the start that it goes open source as soon as possible and can be developed by the international community. The students also told me that this is part of the reason they picked it, because it is attractive to be able to actually do something which is useful for somebody and not just a sandbox project. And this is the signal flow grapher. I have now already put the GitHub link there for you. Here it is if you look at the Google Chrome. So if you go to GitLab, Hansby42 signal flow grapher, you will find the thing to download and an installation instructions. What we have not been able to do yet is make an installer. We simply don't know how. If anybody among you knows it, please tell me. But don't tell me that there is a make an executable in Python, because that doesn't work here. That we tried, the straightforward ones. But you are all engineers, so I'm sure you will be able to install it and then start it from the command line. But be very careful. This version still has some issues and may crash. Be careful and save often. So just that. And if you find any issue, tell me, because this is still very much under development. Having said that, it is already very, very good as it stands. So I will now show that, just to check whether the tool does the right thing. No, it doesn't. Yes, it does. Now you see the signal flow graph. And now I will simply go and make the same graph for you, which I did before. So you can now double click and put the nodes here. How many nodes did I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If you want, you can name them. So this is X in the script. This is Y. But really it doesn't matter whether you give them a name or not. So why does it not matter? And the reason is very simple, because we are here now talking about equations and functions. And you must have seen somewhere somebody writing a mathematical function as f in brackets and then just a dot. Because really, if you do mathematics, it does not matter at all what the variable is called. It doesn't matter. You can call it anything. You can also replace it by a point, by a dot. And if you do analysis with the signal flow graph, you can simply not name it. It doesn't matter. As long as it is uniquely identified, which it is graphically, it doesn't need a name. So names, they are not important in mathematics. You must not know that already, I think. But here you see it very transparently. You can draw the whole signal flow graph without naming any nodes, because nodes, they mean nothing. They would just carry names for you to remember what you meant. Yeah? But other than that, the names are completely unimportant. But the branches are not, because the branches you put, they contain the weights and tell you what the system is doing. So now I do the branches. The easiest way with that tool to do that is mark one node and then just control-click on the next. And then you can draw all the branches. Now I do the loop back, and I also have a loop from that node to that one. I have a loop from that node to that one, and then I would have another forward branch from here to here. And this I don't want to have at the top. So if you click the branch, you can place your spline handles to wherever you want them. And then you would have the, now I save. I said save often. And then you have what you have. Maybe this. You can also move it on the canvas if you want. So, and now this is A, B, C, D, E, the weights of the branches. Now B, C, D, E. And now the feedback here was H. And here the feedback path is F. That was G. And this here is K. I think this is the correct one. Now this tool can do very many crazy things. One of the maybe most crazy things it can do is generate tickets. So if I do that, I will not show it now, then it will write you out the LaTeX file with exactly that graph, which you can use for your documentation to include. But that's just the additional bonus. Yeah? What it can do is calculate the Mason rule for you. So if I mark the input and the output and make generate Mason, now this the people on the internet cannot see because this window is not visible. I will also now, it has also now copied this output to the clipboard, so I switch over to the Google Chrome again, where I have a Python notebook running. So this is what the tool did. And here it called that T, but maybe I now call it G. So if I execute that and display this Mason gain, it needs some time to run because the Python kernel was not started yet. Yes, but now you see the transfer function. Share screen, what I did. Ah, the camera was there, sorry, thank you. Yeah. Somebody called me, yeah. So I forgot to share the screen. Everybody online, I do apologize. So I just clicked together the signal flow graph here, and then made generate Mason. by choosing X and Y. I do that again. If I now do the generate Mason, then it will generate the Python code for symbolic Python. That was the code it generated here, which, okay, I think I need another break. Again, I didn't show it on screen. It needs a lot of concentration. I have to look at the people in the room and think about what I'm teaching and control the live stream. So this time you see it online. Sorry, guys. I checked whether this is really true. Yes, it is really true. So what I did, I drew the whole signal flow graph. I clicked on the input and the output node. I pressed generate Mason, and then it copied the Python code into this Jupyter notebook, which I can evaluate, and then I get the transfer function, which is the same transfer function as I get in the script. But the really nice thing about the tool is, and this was also part of what I told the students to do, is that it will actually write out Mason for you. So it writes out the determinant. You can check whether you found all of the loops. It writes out the paths and the subdeterminants, and it writes out the loops. It writes the numerator and the denominator, which it would like to do for you. So if you have all that, you can draw any graph and check whether you found out all the loops and check whether you found all the forward paths. So now this is the very condensed thing of having the signal flow graph, the Mason graph, very condensed formula. It doesn't help you anything right now because it is meaningless, so it's just A, B, C, D, F. We will make very meaningful examples very soon. But let me first show you one thing more that the tool can do. These are, after all, only equations. So for example, this node here, I can call this variable t. And now I have a signal flow graph, which is an equation system, which has these nodes here, 1, 2, 3, 4, 5 nodes here are dependent variables, and there is one independent variable. So I have a linear equation system with 5 equations. Now, what you always can do if you want to solve an equation system is you can eliminate variables. So for example, you can say I want to eliminate the variable t, so I solve one equation for t and insert the t into all of the other equations. The tool can also do that graphically. I can press eliminate node and it is gone. But now you get an equation where one variable depends on itself. I can eliminate the self loop. Then I eliminate this variable. I again have self loop. I could eliminate this variable also. It gets simpler and simpler. Eliminate this variable. I have another self loop. And now here I have parallel paths, combined parallel. Again, combined parallel. And now I have graphically simplified the equation system. Now it's just y equals something times x. A little bit hard to read because the label here is too close. But if you now look at this formula you have here in detail, you will find that this is exactly the same formula that you got from Mason's gain rule. How can it be something else? It must be the same. And therefore, what you can do if you eliminate variables and stuff like this and simplify equations graphically, you can get the feeling for what Mason's gain rule is actually doing. And as far as I know is that Samuel Mason found the gain rule in much the same way, just much, much, much more slowly on pen and paper. Okay. So these would be the signal flow graphs. Have fun with the tool, I'd say. Let's see how many undo steps I can do. There's also an undo functionality. So that would be it. I will also upload this. You can save it. I saved that, and I will upload it for you. Good. And all of this is quite okay, but if we really want to use that, then we have to think about some applications which will now come next. Let me show you one thing first here, which is a little bit stupid. So there is one bug the system also still has. It is a known issue that a shift of the canvas here, it will not be represented when you save. So I open it again. This is just a trick you need to know right now. I open that again. And now you see that everything is off grid because I shifted a bit. So you press Ctrl A to select everything and pick one of the nodes and move it back on grid. And then you have it nice again. Yeah. Maybe we will solve that. This is not the most pressing thing we should solve. A much more pressing thing is that some node weights are not okay. If I call this node N, capital N, and then I try to calculate anything with that, I will afterwards be able to restart the tool because now it crashes. N is an implicit function of symbolic Python, and the tool does not check everything yet, so occasionally you will call a branch something which doesn't mean what you think it means, and then it will just go bomb. There are 2 or 3 other things you can do which will let the tool crash, so just save often, okay? But now let me go to an example, because that's actually the easy thing, yes? If you have learned what the Mason gain rule is and how to execute it, especially with the help of that tool, you will get a very good experience about loops and forward paths. This is just solving equations, straightforward. But it has always been one of the major feats of electrical engineers to actually write down the correct equations for an electronic circuit. And I'm sure that when you did your some projects or tried some things to do analog circuits with equations, linear equations, you always end up with the problem that then it doesn't work very well because you have an equation missing, or you have one too many, or something like that. Yeah? But with a signal flow graph, you do not actually have that problem very much, because with the graphical representation, if you have one equation missing, you have a hole in the graph, and you will see that this graph can impossibly be that system. It is absolutely impossible to have an equation too many, because this would be 2 parallel paths which do not make sense. So with the graphical representation, you are much more sure that what you do is actually correct. But what do you have to do? And this I show you on the next part of the lecture notes. Now this is very much improvised because I wanted to do it on the blackboard, but here it's not very possible. Yeah. Let's check. Yeah, everybody can see the PDF annotator. Yep. Here in the lecture notes, you now see a very simple circuit with one operational amplifier and 2 resistors. And now there are several ideas which you can pursue in order to do that. One is the very straightforward idea, that is, say I have distinct voltages. Here I would have the Vin, the input voltage. I have the output voltage of everything, and then obviously one other voltage which is very important for the whole circuit is Vx, here in the middle. So let me draw that in the signal flow grapher. In the signal flow grapher, I place for you a now a little bit, I have more space here. So let's make a Vin. And here I name them such that you will remember what it is. I have a Vx and I have the V out. Okay. So this would be okay. And now one of the equations I can already be sure what it should be, because the op-amp itself has a definition here. It amplifies the inputs with plus A and minus A, and therefore makes you the output. So from the Vx to the V out, I have a gain of minus A. So I go here from Vx to V out, and then I have a gain of minus A. But now there are two other paths which I have. So something will come from the input to Vx, and something will come back from the output to the Vx. And the question now is, what? Could somebody close the door, please? So the question is, what should that be? And there you should use the source superposition theorem normally. Are you familiar with the source superposition theorem for linear circuits? It means that if you want to know what happens, you can use all of the sources independently, while all of the other sources are switched to 0. Now the way we have partitioned this circuit here is that we have two sources in here actually, not one. Very often people ask me what is the second source, but I have one source here which is obvious, the input voltage source, but there is also a source at the output of the op-amp, because that is, if you draw that triangle, you mean it to say that this here is actually a voltage source at the output. And you have a voltage source at the output. So let's do the source superposition first. So let's say the input here is just the voltage V in, whereas the other side is presently switched to 0. And I have seen to it that I drew the whole thing here in the lecture notes in the same kind of geometry, such that you see what I have here now is just the op-amp is doing nothing. It does a voltage of 0. So therefore, you have a voltage V in, which goes over two resistors. And those two resistors, they simply are a resistive divider. Now, of course, you know the resistive divider formula, don't you, for resistors? Yeah? It's R2 divided by R1 plus R2. For conductors, it's similarly simple. It's G1 divided by G1 plus G2. That would be the formula you see here. So I have, for the situation where the input source is driven and all of the other sources are 0, I have now the Vx, which is G1 divided by G1 plus G2 times the input voltage, because this is simply voltage divider. So I go over to the graph tool and just write that into here. So G1 divided by G1 plus G2. Okay, this is the weight. Let me go back to the lecture notes. That was one part of the source superposition. The other part of the source superposition is, of course, if I drive the output and set all other sources to 0. And then you see that you get exactly the same circuit, but just driven in the other direction. So again, in this situation, driving a voltage at the output of the op-amp just will cause a voltage at Vx. It is again a voltage divider. It's just that this time it's G2 between the two nodes, not G1. So therefore, I would get almost exactly the same path weight. It's so similar that I'm too lazy to actually type it again. I copy-paste and call this G2. So what I have here is already the final correct signal flow graph of this operational amplifier. And if I evaluate Mason's rule, I will now make this copyable here. So this is a trick I sometimes do. I just put another branch here. Then I have to call this something, because the tool will refuse to make any Mason calculation if there is a single branch in it which doesn't have a weight. But now I can generate Mason and then copy just the result out. And that people online didn't see, but now I copy it in here. And then this serves me as a reminder what the transfer function of that circuit is. Good. But this is not everything. What you very often have in an op-amp, sometimes you want to know what happens here at this node Vx. If this is a really, really good op-amp with an infinite gain, then what you have at this node Vx here is a virtual ground. That's what you learn. There the voltage is zero voltage difference, isn't it? But of course, this is only true if the gain is very large. If it is not very large, what you have there depends on the input voltage. And now it comes. The whole thing I just showed you doesn't make a lot of sense to do it in this complicated graphical way if all you ever want is a single transfer function. But now I want both. I want to know what happens if I also have something at Vx. What happens at Vx? So I'm interested in the transfer function from the input to Vx. Again, I put a reminder branch here. And now I tell it to generate the Mason from the input to there. And of course, the denominators of the two functions, they must be exactly the same, because the denominators of the two functions, they only depend on the loops of the transfer function. If I take another output, the loops don't change, do they? So two functions have exactly the same denominator, but they have a different numerator. So for one of them, the transfer function from the input to the output, the numerator contains the gain, and I will not bore you with calculating the limit. If I take the limit here for a to infinity, you see that it is minus G1 divided by G2 as it should be for the circuit. But at the bottom thing, the gain of the op-amp is only in the denominator. So if I put a to infinity, then I get a situation where this is 0, so my Vx becomes the virtual ground. And this is how I would like you to use that. It goes even further. I have another wonderful trick. And then I will just I will check whether somebody asks something. Not yet. And I have another wonderful trick, which is not quite so in the lecture notes. What you can also do, and this I just show you today, I will go into more depth here later. But this is when you have noise in the amplifier. So for example, let's say you have a noise source in this amplifier. I draw it here. And this is Vn, the voltage noise input referred. I can now draw that also as an input. And if I have this input referred voltage noise, then this will of course have an effect on the output. But what is the effect it will have on the output? Because it is referred to the input of the operational amplifier, this input referred noise will be multiplied by the gain A. That's what input referred means. It means to the output it will be amplified, isn't it? So I go over to the signal flow graph tool, and now I add this here. I put the node which is Vn. From the node Vn here, I would have a path to the output maybe make it a little bit nicer. Okay. And then the weight of that path is A. And now I can, if I want, make another reminder branch from Vn to the output. So, and now I calculate the Mason gain from here to the output. And it's needless to say that it will again have the same denominator. But the numerator again is different. So what you see here in this circuit already, with after we have got that far, is that the gain from the input to the output depends on the resistors. If you choose all of the resistors to be the same, and A goes to infinity, this is -1 if we insert. Here it is 0, so you do not have anything happening in Vx. But this here would be +2. So already from this short study here, we know that in the op-amp configured like this, the noise is amplified more than the signal. But there I will go much deeper in the second lecture. The only thing I want to do now with the signal flow graphs here is to show you an even better way to draw the graph. But first, do you have any questions about how I developed that graph? How I came from the circuit to the graph? Did you understand the source superposition? Please also write something on the chat if you want. Yes, please.
If you're talking about currents, then the A can be replaced with the transconductor.
If it is a transconductor, you have to do it different. I will come to that. Yeah. But it's not so simple, because a transconductor has a current source at the output, not a voltage source, so then the rules are a little bit different. But that is the next step. You had a question?
Yeah, for the noise voltage source, why do you connect it in this way times A?
That also I wanted to say later, but I will just say the question has now come, because I believe in physical models. Everybody says that the noise voltage source of an operational amplifier is input referred. That's how you read it in the textbook. But do you think it comes out at the input, the noise?
Usually it comes from resistors, right?
Oh, no, that's the resistive noise. Oh. But the noise the op-amp itself generates, if you read an op-amp datasheet, it will tell you it has 4 nanovolts per square root of hertz input referred noise. And it's always called input referred noise. But the op-amp has input terminals and an output terminal. And the noise does not come out of the input terminals. It comes out of the output. Yes. So this I want represented in the graph. I know there are so many shortcuts in the textbooks, electronic textbooks, where people then take the noise source and put it in series to either the positive or the negative input. That's the normal way you see it in the textbooks when you deal with noise. I think this is so stupid. Why would you make a model which is non-physical? Can this in any way help you with understanding anything? Now the noise of an op-amp comes out of the output, period. Everything else is not true. But it helps you think about it being input referred, because it makes it easy for you to compare to a sensor. So for example, if you have a sensor that generates 4 nanovolts per square root of hertz of noise, and then you have an op-amp which has 10 nanovolts per square root of hertz input referred, you do not have to do a lot of calculations to find out that this is the wrong amplifier for your sensor. This is why the input referred quantity is important, to get a very quick overview from the data sheet to your application. But actually going and draw the source at the input is beyond stupid, I believe, because why do a non-physical model? I have one student here who already had me before. He's the one who's smiling most. I thought about you. Oh, yes, of course. Another point is when people smile, we have to mask. This is clear, we have to mask, and then you don't see the mouth. But every human being except the psychopath smiles with the eyes also, and I can see your eyes. Of course, you can put the mask like this, then I don't see you smile. But people smile with the eyes, so there you go. Okay. But there you have earned a second break. We will continue in about 15 minutes. But I will just tell you before we go on the break why I would do that. And the reason I want to do that is that this is quite awkward still. I do need a break. So what I could show you here is I took the circuit and I used the source superposition theorem to have to simplify it enough such that I get a simplified circuit here. And then I was able to write down the circuit equations because I remembered the transfer function of the simple voltage divider. Yeah, but what if you didn't remember that? Do you then have to stop the analysis? Of course, everybody remembers that, but imagine that there is a very complicated RC network there. What do you want to do? Have a table of all the possible RC networks. There were many papers written like that in the past where these tables were included. But that's not what I think is good. What I want to do is to have a method which permits me to analyze anything without having a textbook with me. I don't want a textbook. I want to do it just with what I have in my head. And now, what I find when I do this source superposition is that the more voltage sources I have, the easier it will get, because then the circuits between the voltage sources get simpler. So what I will do after the break is simply go the full way and say I put one voltage source in every node. Just like that. Of course, they cannot be standard voltage sources, otherwise the circuit will do something different. They will be magic voltage sources, which I invented in that way, such that they know what I should do, such that they are there. They fit the source superposition theorem, but do not change the behavior of the circuit. This is what makes them magic. So let's take that up after the break. And then you will have everything you need for being able to analyze your own circuits.